Hello students, myself M.M. Dikshit sir, Bhogavati Mahavidyalay, Kurukli. Welcome in the second lecture of the chapter Rotational Dynamics. Our today's point is the kinematics of the circular motion. Before going to this point, let us know about the kinematics of the circular motion. The kinematics is the study of circular motion without considering the action of force on the particle performing circular motion. And for the clear understanding of this kinematics, we compare the physical quantities in the circular motion with the physical quantities in the linear motion. Our today's point is the kinematics of the circular motion shown here. And in the first bracket, the quantities from the circular motion are shown, and these are angular displacement theta bar, angular velocity omega bar, and angular acceleration alpha bar. And these quantities are analogous. This word is very important, shown here, with the quantities from the linear motion shown in this bracket, and these are displacement s bar, velocity v bar, and acceleration a bar. The word analogous is important. It shows that the quantities from circular motion are similar like quantities from the linear motion. A better understanding of the kinematics of the circular motion, we must know the analogy between the physical quantities from the circular motion shown in this first column of the table with the physical quantities from the linear motion shown in this second column of the table. Now, if we are able to use these quantities for the description, then we are able to understand the analogy as well as understand the kinematics of the circular motion. Now let us see how these physical quantities are used to describe the circular motion. In this diagram, particle performing circular motion with center O and radius R is shown, and in this diagram the motion of a body along the straight line is shown. That means this is a phenomenon of linear motion and this is a phenomenon of the circular motion. Now see how this first quantity is used to describe this phenomenon. Now first question is, where is the particle? And therefore the position of the particle along the circumference is described by using this first physical quantity called as a radius vector, and it is defined as a vector drawn from a center of a circle to the position of the particle. Let A be the position. It may be any point on the circumference, and therefore radius vector is used to describe the position of the particle on the circumference. Now, the similar quantity used in the linear motion to describe the position of the body performing linear motion. Where is its initial position? Is described by using a position vector. It is used to describe the position of a body in space by using a frame of reference, and it was already studied in the 11th standard. Now the next physical quantity is angular displacement. The question is, where is its position after time t? Is it here, here, or here? Can be described by using the physical quantity angular displacement theta bar, and suppose that B is the final position after time t, and therefore the change in position of the particle is described by using angular displacement in the phenomenon of circular motion. Similarly, if this is initial position of the particle, then where is its final position? Is described by using the physical quantity displacement. Now another question is, how the angular displacement changes? Is it slow or fast? Is described by using a physical quantity angular velocity. Similarly, in linear motion, how the displacement changes, slow or fast, is described by using a quantity velocity. Now the next question is, how the velocity changes, increases or decreases? That means the change in angular velocity is described by using the physical quantity angular acceleration alpha. And similarly, how the linear velocity changes in the phenomenon of linear motion is described by using this quantity. Now in this discussion, we compare the physical quantities from circular motion with the physical quantities with the linear motion, because we are already familiar with the phenomenon of linear motion, and therefore if we compare the physical quantities from circular motion with the linear motion, then we are able to know exactly the meaning of these quantities in the circular motion, and therefore we are able to understand the kinematics. And for the better understanding the analogy between these two phenomena, let us see the next video.
I want to overview a little bit the ideas of theta, omega, and angular acceleration. You're already noticing that there are some analogs. This is circular motion here, and linear motion has the idea of position also, and that's an x. Linear motion has the idea of a velocity. This is angular velocity, and so linear velocity is a v. And circular motion has an angular acceleration, and the analog is, of course, linear acceleration, or a. So we need to practice this a little bit before we're really good. You know that counterclockwise motion is positive, and that's always the case. I know in linear motion we've talked about your freedom to set up which direction is positive, but in circular motion, anything angular, we're going to be limited by the fact that counterclockwise is always positive. So this way is positive. So if I spin the wheel this direction, then we have a positive theta. Theta is increasing. In fact, theta can increase arbitrarily. Let's start with theta equals 0 right now on the x-axis. And as the arrow moves, I'm going to get theta equal to 1 radian, about there. That's about 57 degrees. And I'm going to get theta equal, ooh, do you know if I go half a rotation what theta is equal to? Let's see, it's half of a circle, and a circle would be 2 pi radians. So that's pi radians halfway around. And here's 2 pi radians, and here's 3 pi radians, and 4 pi radians, 5 pi radians, 6 pi radians, etc. So that's how theta works. But what about angular velocity if there is an angular acceleration? I want you to consider this motion, and I'm going to actually let it slow down deliberately. I'm going to give it a start, and it will be going this way, but slowing down. Okay, so it went this direction and it slowed down. First of all, we can say that omega was positive, right? But what about the change in omega? D omega dt. Was that also positive? D omega dt, let's do that experiment one more time. The thing I'd like you to consider is this. It's going and slowing down because of friction. So d omega dt is actually negative. And d omega dt, well, that's the same thing. D omega dt is the exact same thing as angular acceleration. So that's what we find, that if angular velocity is positive and angular acceleration is negative, then we have something slowing down. This is probably very similar to linear motion. Let's set this up in a slightly different way. I want you to consider omega being less than 0. So now I'm going to be going this direction. Here we are, going this direction. But friction, again, will slow down the spinner. Okay, so it was going this way. Omega is less than 0. But which way was it accelerating? D omega dt. Was it accelerating in this direction or in that direction? What do you think? Got an idea? I think the acceleration was in fact greater than 0, and the angular acceleration is alpha, the Greek first letter. So we've got d omega dt being greater than 0 and omega being less than 0. That means that it's going to be slowing down as well. This is akin. This is, in linear, we have a very similar situation where if velocity is positive and acceleration is negative, that's slowing down, right? And of course, if velocity is negative and acceleration is positive, that's also slowing down. So I'll try to show a quick example of things speeding up, and then we can move on to something more meaningful. If we have, let's say I want omega to be greater than 0 and angular acceleration to be greater than 0. So I'm going to start out going this way, but I'm going to speed up. This is a little bit hard to do, but yeah, going faster and faster and faster. Because it's accelerating in the direction it's originally spinning. So I would expect that the derivative of the angular velocity would be positive as well. Okay, so the cool thing is, with all of this nonsense, we finally have, you know what? There's an equation in kinematics that I call the definition of acceleration. So I'm going to write down angular acceleration. I'm going to tell you that it is delta omega over delta t, which is a little bit sloppy way to write it, but you know that that's omega final minus omega initial divided by time. So I can solve this for omega final, and it says omega final is, well, I guess omega final is equal to where you started plus your acceleration times time. And this looks really similar to final velocity is initial velocity plus acceleration times time. In fact, all of the equations that you know and love are here and they're all going to be the same. So let's write out all these equations. We've got 4 kinematic equations, and you know them all, and we're going to have all the same kinematic equations for angular motion. So the first one that we wrote down was the definition of acceleration, and that's v final is v initial plus acceleration times time, and this is the linear side for us, and we'll do the angular side. The angular or circular side will be over here in red, and the analog for that equation is omega final is omega initial plus angular acceleration times time. Cool. And another equation that we could consider. Let's say final position is initial position plus, what do we got? We got initial velocity times time. I'm going to drop out these delta t's, that's kind of silly stuff, plus 1/2 acceleration times time square, and that equation appears angularly also as theta final equals theta initial plus initial angular velocity times time plus 1/2 angular acceleration times time square. And there's another one, says that final position is, well, I guess it's initial position. We got to consider where we start, right? Initial position plus 1/2 initial velocity plus final velocity. This is 1/2 initial plus final is average. So it's average velocity times time. And that's got an angular analog that looks like this. Your final angle is the angle at which you started plus 1/2 your initial angular velocity plus your final angular velocity times time. All the same. Final velocity square, tail of 2 squares, is initial velocity square plus 2 times acceleration times change in position. Has another analog here, that is omega final. The final angular velocity square is equal to the initial angular velocity square plus 2 times angular acceleration times change in angle.
Now the direction of angular velocity omega shown here is explained in this paragraph shown by the bracket here. We may think that the direction of the angular velocity omega is in the plane of the circle, but actually it is perpendicular to the plane of the circle and along the axis of rotation, and it is shown in this diagram, and it is determined by a right hand rule. The necessity of the use of a right hand thumb rule will be explained in the next video. Let us understand the right hand thumb rule, and our volunteers are Tanishka Dixit and Atharva. Now tell me the direction of, Tanishka, tell me the direction of revolutions of the blades of the fan.
Clockwise.
Atharva, tell me the direction of revolutions of the blades of the fan.
Anti-clockwise.
Yes, and it shows that the direction of revolutions depends upon the positions of the observers. For this observer, if it is clockwise, then for this observer it is anti-clockwise, and therefore it is necessary to use the right hand thumb rule. And as already stated, the direction of angular displacement and angular velocity is along the axis of rotation passing through the axle of this fan. But whether it is towards left or towards right can be determined by using the right hand rule as follows. Tanishka and Atharva, curl your fingers of the right hand and stretch the thumb outstretched. Show there your direction of curled fingers in the direction of the revolution of the blades of the fan and held the hand with thumb outstretched. Now it shows that the direction of angular displacement at it is along the thumb, then it is towards right, and for Atharva it is also towards right. Even if for both observers the direction of revolution is different, but the direction of angular displacement is same. It shows that the use of right hand thumb rule is necessary to determine the direction of angular displacement, and it shows that it is independent on the positions of the observers. The use of right hand thumb rule to determine the direction of angular velocity and angular acceleration in case of the horizontal circular motion. The previous motion is vertical circular motion. So we are going to use the right hand rule in case of horizontal circular motion. Already we know that the angular displacement and velocity is along the axis of rotation and perpendicular to the plane of revolution. But whether it is vertically upward or downward can be determined by right hand thumb rule. Atharva, tell me the direction of revolution of the object placed on this turntable.
It's clockwise.
Good. Now hold your hand on the table at the center of the rotating table with fingers curled and thumb outstretched. Now if the curled fingers denotes the direction of the revolution, then the thumb denotes the direction of angular displacement and velocity. And as it is vertically downward, so in this case the angular displacement and velocity is vertically downward, and so it is taken as a negative. So we conclude that for clockwise rotation angular velocity is taken as a negative. Now Tanishka, please change the direction of the revolution. Atharva, which is this direction?
It's an anti-clockwise direction.
So let us use the right hand rule. In this case, hold your hand at the center of the table with fingers curled in the direction of revolution and thumb outstretched along the axis of rotation. Now in this case the curled fingers denotes the direction of revolution and thumb denotes the direction of angular displacement. It shows that the angular displacement is in upward direction, and so for the anti-clockwise revolution the angular displacement and velocity is taken as positive. Now the next point is uniform circular motion, and the definition of the uniform circular motion is shown in this bracket. During the circular motion, if the speed of the particle remains constant, it is called uniform circular motion, and it is abbreviated as UCM. As UCM is periodic motion shown here, then for the numerical point of view, the formula for period and frequency shown in this bracket is very important. Also, as in UCM only the direction of the velocity changes, so the acceleration is only a centripetal or radial acceleration. And for the numerical point of view, the formula shown in this bracket is very important. It is shown in different forms. Not only the formula of the centripetal and radial acceleration, but also the direction is very important, and it is shown in this diagram. It is along the radius and towards the center of the circle shown in this diagram. But I would like to explain you why the radial or centripetal acceleration is along the radius and towards the center, even if it is not in your syllabus. Let us see this direction in the next video. For the direction of radial or centripetal acceleration in UCM, consider a particle is performing uniform circular motion. With center O and radius R. Suppose that initially particle is at point A. We know that UCM is an accelerated motion, and it is due to the change in direction of the linear velocity, but not magnitude. And therefore, in order to know the direction of centripetal or radial acceleration, we draw this vector diagram. So the linear velocity at point A is along the tangent, and it is denoted by AP bar. Suppose that a particle moves from point A to the point B in a short interval of a time delta t, and this is a angular displacement delta theta. And when particle is at point B, then the linear velocity at point B is represented by the vector bq bar. This diagram shows that when a particle is at point A, the linear velocity is along AP. When it is at point B, it is along BQ. And between these 2 points, where is the resultant change in the direction of velocity, that is delta V, is we are going to determine. And therefore, we draw a perpendicular BR bar. We draw an arrow BR bar equal and parallel to AP bar to determine the direction of resultant velocity. And by applying the triangle law of vector addition, the resultant change in direction from A to B is represented by this vector RQ bar. So this diagram shows the change in direction of the velocity, that is delta V. But if the time interval delta t is reduced to half, then the point B will be at this point. Again, if it is reduced to half, then point B will be at this point. And so if the time interval delta t is continuously reduced, then point B approaches towards the point A. And when time interval delta t tends to 0, then point B is very close to the point A. And therefore this vector of change in velocity is at the instant of delta t tends to 0 is along the radius and directed towards the center. And as the change in velocity is along AO bar, therefore the acceleration is also along AO bar and it is represented by AC bar. And this discussion shows that the instantaneous acceleration in UCM is along the radius and directed towards the center of the circle. And as it is along the radius, it is called as a radial acceleration, and due to the towards the center, it is also called as a centripetal acceleration. For this point, illustration of the circular motion of any particle of a fan rotating uniformly, let us see this video. This is our next point, non-uniform circular motion. During the circular motion, if the speed of the particle changes, then it is called non-uniform circular motion. And in this point, we shall consider two sub-points. First is the direction of angular acceleration, and the second is the direction of tangential acceleration AT bar. Let us consider first the direction of angular acceleration alpha bar in non-uniform circular motion. The direction of alpha bar is also along the axis of rotation and perpendicular to the plane of the circle, and it is taken as a positive if the angular velocity omega bar increases, shown in this first diagram. And if the angular velocity omega decreases, then the angular acceleration alpha bar is taken as a negative along the axis of rotation, but opposite to the angular velocity omega. It shows that the right hand rule is not used to determine the direction of angular acceleration alpha, even if it is along the axis of rotation and perpendicular to the plane of the circle. In the next video, I would like to explain the direction of tangential acceleration, even if it is not discussed in this book or in your textbook, but the formula which is very important for the numerical point of view is based on the direction of the tangential acceleration AT bar, which is given in the next video. When the particle is performing non-uniform circular motion, then the resultant acceleration has two components. One is centripetal or radial acceleration, and second is the tangential acceleration AT bar. Let us see the directions of these components of the resultant acceleration. Consider a particle is performing non-uniform circular motion in a horizontal plane. We already know that the centripetal acceleration AC bar is along the radius and towards the center of the circle, and the tangential acceleration is along the tangent. It is represented by AT bar. As it is along the radius and it is along the tangent, so the angle between them is 90 degrees. Therefore, the resultant acceleration is represented along the diagonal and it is represented by a bar. This is the resultant acceleration a bar, and the diagram shows that it has two components. One is centripetal acceleration AC bar and another is a tangential acceleration AT bar. Therefore, the resultant acceleration A bar is expressed as AC bar plus AT bar. So, the resultant acceleration has a two component, a centripetal acceleration AC bar and a tangential acceleration AT bar. This centripetal acceleration is responsible for the change in direction of the velocity, and as it is along the center, it is called as a centripetal acceleration. And this tangential component changes the magnitude of the linear velocity, and as it is along the tangent, it is called as a tangential acceleration. For the numerical point of view, the magnitude of the resultant acceleration is important, and it is given by A is equal to square root of AC square plus AT square. The another terms are absent because angle between them is 90 degree, and second is the tangential acceleration AT bar. Let us see the directions of these components of the resultant acceleration. Consider a particle is performing non-uniform circular motion in a horizontal plane. We already know that the centripetal acceleration AC bar is along the radius and towards the center of the circle, and the tangential acceleration is along the tangent. It is represented by AT bar. As it is along the radius and it is along the tangent, so the angle between them is 90 degree. Therefore, the resultant acceleration is represented along the diagonal and it is represented by A bar. This is the resultant acceleration A bar, and the diagram shows that it has two components. One is centripetal acceleration AC bar and another is a tangential acceleration AT bar. Therefore, the resultant acceleration A bar is expressed as AC bar plus AT bar. So, the resultant acceleration has a two component, a centripetal acceleration AC bar and a tangential acceleration AT bar. This centripetal acceleration is responsible for the change in direction of the velocity, and as it is along the center, it is called as a centripetal acceleration. And this tangential component changes the magnitude of the linear velocity, and as it is along the tangent, it is called as a tangential acceleration. For the numerical point of view, the magnitude of the resultant acceleration is important, and it is given by A is equal to square root of AC square plus AT square. The another terms are absent because angle between them is 90 degree and AT bar is perpendicular to AC bar, and therefore other terms are absent in this square root. Up to this point, we studied first point, kinematics of the circular motion. Second point, the direction of the angular velocity omega. Third point, uniform circular motion. Fourth point, the direction of radial or centripetal acceleration. And fifth point is a non-uniform circular motion and the direction of angular acceleration alpha and a tangential acceleration at bar. So up to this point we studied the main point, the kinematics of the circular motion.
One, start.
Now write down the following questions in your notebook. The question number 1 is what is kinematics? What is kinematics of the circular motion? Second point, give the direction of angular velocity omega, bar. Third question is state right hand rule. Fourth question is define UCM and non-UCM. Fifth question is give the direction of centripetal acceleration. In C bar, comma, tangential acceleration. Next is angular velocity and angular displacement and angular acceleration, etc. Now the sixth question is give the formula. First is period of UCM in bracket capital T. Second is frequency of UCM in bracket small n. Third is angular velocity omega. Fourth is centripetal acceleration. Centripetal acceleration in different forms. Now your homework is to extract the answers of these questions from this lecture, and the next point will be discussed in the third lecture. Thank you.